In this video we will understand the linear regression model training using batch gradient descent method. In the first part of the video we'll see the working of linear regression model theoretically, and in second part we'll code it from scratch without using scikit-learn. Here's the intuition behind this equation. Theta 0 is the intercept or bias term. Think of it like a starting point for our predictions. It shifts the model's prediction up or down. Theta 1, theta 2, up to theta n are the coefficients or weights. These control how much each feature contributes to the prediction. If theta 1 is large, the feature x1 will have a bigger impact on the result. x1, x2, up to xn are the input features, which are the variables or data we use to make our predictions. This equation shows how we make predictions. The predicted value, or the output we want to find, is represented by y hat. We get this predicted value by combining the input features, like x1, x2, and so on, up to xn. In simple terms, this equation says that the predicted output is a weighted sum of the input features, where each feature's importance is determined by its corresponding coefficient. Now, we can represent this equation in a more compact way, using vectors. This vectorized format is just a more efficient way to handle the calculations. Instead of writing out each term individually, we group them together. Here's how it works. X is the feature vector, which includes all input features like x1, x2, up to xn. This is usually written as a column, including a 1 for the intercept term. Theta is the parameter vector, which includes the coefficients for all the features, including the intercept. In this format, the dot product of theta transpose and x represents the weighted sum of the features. It's exactly the same as the previous equation, but written more compactly and easier to calculate with large datasets. The advantage of this vectorized format is that we can compute the predictions for all data points at once, using matrix operations. This makes it much faster, especially when dealing with large datasets. Next, we define the cost function, which helps us measure how well our model is doing. In this case, the cost function is the mean squared error, or MSE. MSE is how we measure the error between the model's predictions and the true values. M is the number of training examples. Xi and Yi are the input features and actual output for the ith training example. Theta transpose times Xi gives us the predicted output for the ith training example. The goal is to minimize the MSE, meaning we want the difference between our predictions and the actual values to be as small as possible. By squaring the errors, we ensure that both positive and negative errors are treated equally. The result is a smooth function we can minimize. To minimize the MSE, we need to calculate the gradient. Specifically, we compute the partial derivative of the MSE cost function with respect to each parameter. This tells us how to change each parameter to reduce the error. Here's the idea. We want to adjust each parameter in the direction that decreases the error. For each parameter, the derivative gives us the rate of change of the cost function with respect to that parameter. The error is the difference between the predicted value and the actual value, and we multiply this by the corresponding feature value to weight the error by how much each feature contributes. This gives us a gradient vector, which combines the derivatives for all parameters. Instead of calculating the derivative for each parameter individually, the gradient vector lets us adjust all parameters at once. Now that we have the gradient, we use it to update our parameters. This is where gradient descent comes in. To minimize the cost function, we need to move in the opposite direction of the gradient. The gradient points toward the steepest increase of the cost function, so we subtract it from our current parameters. Eta is the learning rate, which controls how big each step is when we update the parameters. The gradient vector tells us how much we need to adjust each parameter to reduce the. By repeating this process over and over, the parameters gradually adjust, and the cost function decreases. Eventually, we converge to the optimal values for the parameters, where the model's predictions are as close as possible to the actual values. To summarize, we've covered how the linear regression equation works, how we measure the error using the MSE cost function, and how gradient descent helps us find the best parameters to minimize that error. The goal of gradient descent is to adjust the parameters step by step to make the model's predictions as accurate as possible. Now let's dive into the code. We're going to build a batch gradient descent regressor in Python. This implementation uses NumPy for numerical computations and matplotlib for plotting our results. Let's go step by step. First, we import the necessary libraries. We use NumPy for numerical operations, pandas for handling data, and matplotlib for plotting our results. We create a class called bgdregressor. This class will implement our batch gradient descent model. Inside the class, we define an initializer, init, method, where we set the default values for the learning rate and number of epochs. The learning rate controls how big each step of gradient descent will be, and the epochs define how many times we will iterate over the dataset to update the parameters. The fit method trains the model using the input data. We start by extracting the dimensions of our training data. M is the number of examples and n is the number of features. We then initialize the coefficients and intercept with random values. These are the parameters that we will adjust during the training process. Next, we loop over the training process for a specified number of epochs. In each epoch, we calculate the predicted output, y_pred, by calling the predict method. Then, we compute the gradient of the loss with respect to the intercept and coefficients. Finally, we update the parameters by subtracting the gradients scaled by the learning rate. We also record the loss at each step, so we can monitor the progress and make sure the model is improving. The predict method computes the model's predictions for the test data. It takes the feature matrix x_test and multiplies it by the model's coefficients, then adds the intercept. This is simply the linear regression prediction formula we discussed earlier. The plot_loss method uses matplotlib to plot the loss over each epoch. By plotting the mean squared error, or MSE, we can visually inspect how the model is converging over time. The log scale makes the progress easier to track, especially when the loss decreases rapidly. Now, let's see how this model works with some real data. We load a CSV file containing data on study time and test scores using pandas. We separate the features, study time, and the target variable, test scores, into x and y, respectively. Next, we create an instance of the BG_regressor class and call the fit method to train the model. After training, we use the predict method to predict the test score for a study time of 2.04 hours. We print the model's coefficients and intercept, which tell us the relationship between study time and the predicted test score. Finally, we call the plot_loss method to visualize how the loss has decreased over the epochs. That's it for our batch gradient descent implementation. We've created a simple linear regression model that uses gradient descent to find the best fit parameters. We also visualized the loss curve to see how well the model was learning over time. This implementation provides a clear understanding of how gradient descent works in practice and how it's used to optimize the parameters of a linear regression model. I encourage you to experiment with different datasets and parameters to see how the model performs in various scenarios. That's it for today. See you all with next algorithm from scratch.